Okay, this video is going to show you how to use the ADC input with the STM32 Nucleo boards. So first, we're going to use the STM32QMX to set all the parameters for the analog input. So first, I'm going to select the board. The board that we're using is a Nucleo 64 L053R8. Double click on this and initialize all peripherals with the default mode. Okay, once we have this, there's a few parameters that we need to set. First, we on the board itself, it doesn't come with the high-speed crystal, so we can disable this input to reset state. Okay, next we have to set the analog input ADC, and for this example, we're going to use the channel 0. So after we select the channel 0, we have to do some settings over here. Clock prescaler will set to default, resolution 12-bit resolution default, data and alignment from the right, and forward scan direction. Since we are going to let it run the conversion continuously, so we use the continuous conversion mode. So we have to enable this. The rest we set to default except for the sampling time. Maybe we would like to set to the higher value so that at least we can confirm that we can obtain the correct raw value. There are three types of conversion. First, we're going to use using the interrupt. Then we'll look into how to use the bipolar method, and lastly, we're going to use the DMA, which is the direct memory access. Okay, so next we got to set the clock. Let's set it to about maybe 16 megahertz. Okay, so you configure all to 16 megahertz, and okay, over here I forgot to say something. Since the first one we're going to show you is using the interrupt, we have to go to the NVIC settings and we have to enable the interrupt. Okay, and we go to the project manager and we use we call this ADC example. And we are using the Cal Microvision, so it's using the MDK arm. And okay, then we generate the code. Okay, open project. Click on the ADC example and look for the application. The codes are in the main. Okay, so we're going to get we got to draw the raw data and put it into a variable. So we have to define a private variable in the private variable user code begin. So let's call, since we're using a 12-bit resolution, we can use the 16-bit. Let's call this ADC value or ADC raw. Okay, in the main, since it's a continuous mode, we do not have to start and restart the process every time. So we just do a start at the beginning before the while loop. So in the user begin code too, we can add how underscore DAC underscore start Okay, over here you see there's three different methods of starting the ADC. The first one is using the polling method. The second one is using the direct memory access, and the third one, which is I'm going to show you now, is using the interrupt. So we're going to put in the ADC pointer. Because this is there's only one ADC, and it's shared among various channels, so that's why we only see HADC. There's no 1, 2, 3. Once we have that, next we have to go into the interrupt C files. Double click on this, you'll notice that the handler for the ADC is right at the bottom, and you look at the how ADC RRQ handler. Okay, we have to compile it once first before we can go into the definition of the RRQ handler. Right click, go to definition of RRQ handler. In this handler, it will settle all the processes, such as to clear the interrupt flag and so on. The one that we are interested in is the callback, conversion complete callback. And over here is a wake function. Wake function means that we can override. Currently in the default callback is empty, doing nothing. So we got to put it into the main. We can put it in the user code begin here. So every time when there's an interrupt call, it will comes to this callback. So over here, what we're going to do is we put the converted ADC value, the analog value, into the ADC raw variable. So what we so we type in ADC raw equals to how underscore ADC get value, and this comes from the pointer from HADC, so we do not need to use the ampersand, because it's we got the value from the function itself. Okay, and that's all. So we compile, make sure there's no error. Okay, and then we do a debug. Okay, this happened because I have to do some settings here. Go to the project, options, debug, and choose preset. We don't need this window, close it, and we can run. But before we run, let's pull out this variable raw ADC. You put it into the watch 1. Right now it's a 000, which will display the 4-bit value. 4-bit value will be up to 0 to 4095. We run, and then we see the values changing. 1 is 6. Right now my voltage is connected to it's not connected. Hold on. Okay, right now it's connected. The pin itself is connected directly to my power supply, acting as a analog value. I've set it to the about 1 volt here. Okay, so let's see what is the 1 volt. So the VCC, the maximum VCC we set is 3.3 volt, and it's 3 bits, so it's up to 4095. So this is the resolution per step, so store it in the memory. Now we look at what's the value for this. Is about 454 about 548. Okay, let's take it as 548. 1352. Okay, 1352. 1352 multiplied by the resolution, memory recall, and we get about 1.09 volt, which is very close to what we have set here. Okay, so this is the first method of using the interrupt. Next, we try to use the bipolling method. Okay, the difference in the polling method is in the QMX, we set the pin configuration, we take away the interrupt. So in the NVIC, we uncheck the enable. Okay, the rest of the parameters remains the same, and we generate the code. Since we're using polling method, we do not need to use the callback anymore. We can delete the callback. And it changed from the start IT interrupt to not using the IT. Okay, but in your while loop, every time when we want to see the values, we have to poll for the completion. So we can type in here if how underscore ADC. Okay, we got to get out of the debug mode first. Okay, how ADC this poll for conversion, and ampersand HADC. The timeout we put maybe 1 millisecond is good enough, and you will return whether is it completed or not completed. So if it is completed, you will return the OK, and if it is OK, we'll put the values into our ADC raw equals to how ADC get value, and this is from ampersand HADC. Save and compile, make sure there's no error. Okay, do a compile in the debug, and we can run. So right now, let me change the value of the voltage. Let's change it to 2 volt here. Okay, now in my meter it shows about 2 volt. The value shown in the ADC raw is about, I would say, A00. Okay, so A00, what's the value? A00 is 2560. So 2560 multiplied by the resolution, and we'll get 2.06 volt, which is quite close to what we have set. Okay, now this is how we set using the polling method. It takes more resources from the microcontroller because every time we have to poll for the completion of the conversion, and we get the data from the memory from the we have to pass the values from the ADC into the memory. Okay, so this slightly more resources compared to the interrupt method. Okay, now the last method is using the direct memory access. So direct memory access, the difference is we instead of using the microcontroller to monitor and to control the the conversion, what we're going to do is that after we set the the conversion, it will automatically send its raw data to a buffer or memory directly, okay, without going through our controller. So by right, it should take the least resources from the microcontroller. So over here we have to set the DMA settings at and at ADC. So over here, instead of normal, we choose circular, which means that let's say we set the buffer of 100. It will, after you complete the buffer, fill out all the buffer, it will continue back to the original place address again and fill up, so that we do not have to every time stop and start the conversion. Okay, so now the memory, we are going to use half word because we are only using 12-bit 12-bit conversion. So 12-bit is equivalent to about equivalent to 12 bits is less than 16-bit. So half word is 16-bit, so this is good enough. Now we go back to the parameter setting, and we choose the DMA continuous request enable. Okay, the rest we set it as per normal. Okay, and generate the code. Okay, over here, instead of just start, we're going to use the DMA. Yeah. Okay. In using DMA, we need to use an array because it's automatic send from the data from the ADC to the buffer. So you have to change this to an array. This is just for example, so I'm going to use just one value, one element in the array. Of course, you can set to like say 1000, so that it keep on filling up the buffer. But I'm setting only one just for example only. Okay, so over here, yeah. So how underscore ADC underscore. Okay, we have to get out from the debug again, which I always forget. Okay. How underscore ADC underscore start. So now we're going to use the DMA. So it says that the first one is the pointer for our the DAC pointer, and then we have to put in the buffer and then the length of the buffer. So the buffer we're using is ADC raw. Okay, and ADC, the size of ADC raw. Okay, one thing is different is, okay, I forget one more bracket here. Okay, okay, let me type in again and let you see. HAL or ADC start. Okay, notice that the buffer must be a unsigned integer 32 bit. So we have to, what we can do is to cast the 16-bit into a 32-bit. It is a pointer. Okay, so everything are the same. We save and compile, make sure there's no error. And we got, And now the while loop inside, there's no code, there's no interrupt. It will directly send from the ADC conversion into the buffer. So let's compile into debug, and so now it's an array. We will run it. Okay, now I set the value to 3 volt. On my meter it says about 3 volt, so the values here is EA2. Okay, so we use a calculator again to find out what is EA2. $3,746 multiply by the resolution, and we get about 3.02 volt, which is very close to what we have set. Okay, so this is how we do the conversion, analog conversion, using the direct memory access. Okay, that's all for the video.